Exploring the microwave and millimeter wave bands is often considered the final frontier of amateur radio. Unlike the HF bands, where ionospheric skip dictates the day, the spectrum above 1 GHz operates by an entirely different set of rules. It is a domain defined by strict line of sight propagation, atmospheric phenomena, and a heavy reliance on custom built equipment. Amateur radio allocations extend far beyond the UHF spectrum, stretching up into the hundreds of gigahertz. The microwave bands 1 GHz to 30 GHz, 23 cm 1.2 GHz, and 13 cm 2.3 or 2.4 GHz, often the entry point for microwave operators. The 13 cm band is notably shared with Wi-Fi, but it is also a primary uplink band for satellite operations. 9 cm 3.4 GHz and 5 cm 5.7 GHz, popular for regional distance records and contesting. 5 cm 5.7 GHz band has been allotted for radio amateurs in VU for a long time, though I am yet to hear of any activity on that band in this region. 3 cm 10 GHz, the crown jewel of amateur microwave. It is highly active for Earth-Moon-Earth communication, terrestrial distance records via rain scatter, and serves as the downlink for geostationary amateur satellites like the QO100. The millimeter wave bands above 30 GHz, 1.2 cm 24 GHz, and beyond 47 GHz, 76 GHz, 122 GHz, 134 GHz, and 241 GHz. Here, wavelengths are so short they are measured in millimeters. Operations are highly experimental, often requiring operators to repurpose commercial telecom or automotive radar components. Propagation characteristics. While HF relies on the D, E, and F layers, microwave propagation is largely dictated by the troposphere, the lowest layer of the atmosphere, and weather events. Line of sight. The foundational rule of microwaves: if the antennas cannot see each other or see the same reflective surface, communication is generally impossible. Tropospheric ducting. Temperature inversions over large bodies of water or flat land can trap microwave signals, carrying them hundreds or even thousands of kilometers beyond the visual horizon. Coastal regions are particularly famous for phenomenal ducting events. Rain scatter. At 10 GHz and above, signals can bounce off heavy rain cells. Operators point their antennas at the storm rather than each other to establish contact. Atmospheric absorption. As frequencies rise, atmospheric gases begin to absorb RF energy. For example, the 24 GHz band sits near a water vapor absorption line, severely limiting its range in high humidity, while the 60 GHz region, just outside ham bands, is heavily absorbed by oxygen. Equipment, the homebrewer's domain. For those accustomed to building linear amplifiers or aligning transceivers on the lower bands, the transition to microwaves requires a shift in hardware philosophy. You will rarely find an off-the-shelf shack-in-a-box that covers 10 GHz. Transverters. Most microwave operations rely on transverters. An existing VHF or UHF radio, often set to 144 MHz or 432 MHz, serves the intermediate frequency. The transverter mixes IF with a highly stable local oscillator to reach the microwave band. Jumping over wiring. At these frequencies, standard coaxial cables suffer from immense loss. RF energy is instead routed through specialized rigid hard line or hollow metal pipes known as waveguides. High gain antennas. Unlike trying to squeeze efficiency out of a wire dipole on a low band, achieving massive gain is relatively easy at microwave frequencies because the wavelength is so small. Parabolic dish antennas and feed horns are the standard. The theoretical gain of a parabolic dish illustrates why they are so vital at these frequencies. It can be calculated using the following equation. G equal to 10 log to the base 10 eta into pi d by lambda whole squared, where G is the gain in dBi, that is decibel to an isotropic antenna compared to isotropic antenna. Eta is the aperture efficiency, typically around 0.5 to 0.6, that is efficiency relative to the real diameter. D is the diameter of the dish and lambda is the wavelength. Because lambda is squared in the denominator, as the frequency increases and wavelength decreases, the gain of a fixed size dish skyrockets. Rover operations. Because line of sight is critical, operators frequently mount their transverters and dishes on vehicles, rovers, and drive to high elevation peaks to maximize their horizon during contests. Satellite communications. LEO satellites and geostationary payloads rely heavily on the S, X and K bands. The high gain of dish antennas easily punches through the ionosphere with minimal power. Earth-Moon Earth (EME). Bouncing signals off the moon is highly practical on bands like 10 GHz because cosmic background noise is incredibly low and antenna gain can be exceptionally high, compensating for the massive path loss.